So we're going to go over some of the problems from homeworks 3 and 4 on vector spaces. So let's begin with homework 3, which is on pages 14 and 15. Good, number 1. Actually, it's pages 13 and 14, I think. So we're looking at the set of all vectors x, y in R2, such that x plus y equals 0. X plus y equals 0 is the same thing as y equals minus x. So that's just the line, y equals minus x in the plane. That's all it is. And if you look at the set of all x, y, where x plus y equals c, then you're just saying y is equal to minus x plus c. So for example, if c is equal to 2, y is minus x plus 2. This is just the line with slope minus 1 and y-intercept 2, just like you learned in high school. Nothing more than that. If we look at problem number 2, I already did this several times in the problem sessions. You look at all x, y, and R2, such that x plus y equals 1. Again, that's just the line. Y equals minus x plus 1. We're just looking at the red line. And if you have 2 points that satisfy that, so suppose x1, y1 is in L, and x2, y2 is in L, and you take a number, a scalar t, and, sorry, let me do it differently. So you want to show that if xy is in L, then you can write xy as a linear combination of the 2 basic vectors, 1, 0, and 0, 1, where the scalars add up to 1, 1 minus t and t. So let's see, what's an easy way to do that? If x plus y equals 1, then x is equal to 1 minus y. So xy is 1 minus y, and you can see, I think, that that's the same as 1 minus y 0 plus 0 y, which is 1 minus y times the vector 1, 0, and y times the vector 0, 1. So just let t equal to y, and you have an expression of this form. That's problem 2. Problem 3 is just to draw another vector subspace, an affine subspace. Sorry, problem 3. So if we're looking at the set of all x, y, such that 5x minus 2y equals 0, again, there are lots of ways to do this. They all come down to the same thing. This says that 2y is equal to 5x, or y is equal to 5/2 x. So this is just the line with y-intercept 0 and slope 5/2. So it looks something like that. When x is 1, this would pass through the point 5/2. So it's just the line through the origin with slope 5/2. And if you had something like 5x minus 2y equals 2, that's just putting c equal 2 on the right-hand side. Again, 2y is 5x minus 2, so y is 5/2 x minus 1. It's the line with slope minus 5/2 that passes, has y-intercept minus 1, has y-intercept -1. So this is y equals 5/2 x minus 1. Of course, another way to do that, if you like x and y intercepts, you have 5x minus 2y equals 2. When x is 0, y is -1. And when y is 0, x is 2/5. So you can also say it's the line that crosses the y-axis at -1 and crosses the x-axis at 2/5. But in any case, it's the same line. There's only one line. Problem 4 is an exercise in artistic skill. If you look at all the vectors in 3 space that satisfy the equation x plus y plus z equals 0, well, you're asking to draw a 3-dimensional object on a piece of paper, which is practically impossible. So you can say, well, of course, it goes through 0, 0, 0, but just try and imagine it. This is the point. If this is the x, y, and z axis, this is the point 1, 1, 0. This would be the point 1, -1, 0. That lies on the satisfies this equation. Actually, it's really, I can't really do it. All you have to do is say, well, there's some plane through the origin. It's actually easier if the right-hand side isn't 0. So if you look at the affine space of all x, y, z in R3, such that x plus y plus z equals 1, then you know certain points that satisfy this. For example, so if we call this space L, x plus y plus z equals 1, you could have 1, 0, 0, 0, 1, 0, and 0, 0, 1. All 3 of these unit vectors satisfy this equation. So in the plane, you take these 3 vectors. This is 1, 0, 0, 0, 1, 0, 0, 0, 1. They form a triangle in 3-dimensional space. And you just extend that triangle, and that's what this plane is. So that's the best you can do with problem 4, but it's an important problem if it makes you think a little bit about surfaces and planes in 3-dimensional space. In problem 5, we have a vector subspace W in Rn and a vector V in Rn. And we want to show that V plus W, if you translate W by V, you don't do anything new if and only if V is in W to begin with. So the proof in one direction is simple. We know 0 is in W. So V plus 0, which is V, is in V plus W. So if V plus W equals W, then V is in W. Every subspace contains the 0 vector. So if you take any vector V, V plus 0, which is V, is in this translated subspace, W translated by V. But if V plus W equals V, that says V is in W. So if V plus W equals W, then V is in W. Conversely, let V be in W. If W is in W, because W is a subspace, it's closed under vector addition. So V plus W is in W, which means the whole translate V plus W is contained in W. For any v plus w is in w. So this translates contained in w. On the other hand, let w be in w, then if v is in w, that means w minus v is in w, because again, a subspace is closed under vector addition and scalar multiplication, which means it's closed under subtraction. Sorry, let v be in w. Then if you take any vector w in the subspace w, w minus v is in w, which means w, which is w minus v plus v, is in, let me write this as w, which is v plus w minus v, is in v plus w. This is a vector in w translated by v. So w is contained in v plus w. And if you have, in general, and for any sets, two sets and each is contained in the other, then they're equal. So that is a good proof of this result. These homework problems 6 and 7 were on the review sheet. I'll do them again. I did them a couple of times in problem sessions. So let's look at 6. We have an affine subspace L equal V naught plus W. That means W is a subspace and V naught is a vector. And we want to show that if X and Y are in L, then this linear combination 1 minus Tx plus Ty is in L for all scalars T. So if X is in L, then X is V naught plus W1. And if Y is in L, then Y is V naught plus W2 for some vectors W1 and W2 and W. So if I take 1 minus Tx plus Ty, that's 1 minus T V naught plus W1 plus T V naught plus W2. If I just distribute across, that's 1 minus T V naught plus 1 minus T W1 plus T V naught plus T W2. Let me just rearrange this. This is 1 minus T V naught plus T V naught plus 1 minus T W1 plus T W2. This is V naught minus T V naught plus T V naught plus this. The W1 and W2 are in W. So W is closed under taking linear combinations. This is some vector W and W. And here the plus and minus T V naughts cancel. I get V naught plus W, which is in V naught plus W. So this linear combination of the vectors X and Y, where X and Y are in the affine subspace, stays in the affine subspace. That's part A, and part B is just the generalization of this to sums of more than two vectors, but this is the essential part. Problem 7 is to show that, well, problem 7, the first part is just, you have X1 is a set with just the numbers 1, 2, 3. X2 is the set 2, 4, 6. And X3 is the set 1, 3, 6. This exercise is just to make sure you understand what intersection means. X1 intersect X2 means everything that's in both of these sets. That's just the number 2. X1 intersect X3, that's everything in these two sets. That's 1 and 3. X1 intersect X2 intersect X3, that's everything that's in all 3 of these sets. The only thing in X1 and X2 is 2, but 2 is not in X3. So there's nothing in this intersection of the 3 sets. So there's nothing in there. This is the empty set. And that's the notation for the empty set. And it's an example of taking some intersections in R2. We have X, which is all vectors of the form X0. That's the x-axis. We have Y, which is all vectors of the form 0, Y. That's the y-axis. And we have H, which is all vectors x, y, where x can be anything, but y has to be positive. If x and y, if this is a vector and y is positive, that means it's everything strictly above the x-axis. It's sometimes called the upper half plane. It does not include the x-axis. It's everything above the x-axis. So if we take x intersect y, this is x, this is y, the intersection is just the origin, 0, 0. Y intersect h, so y is the y-axis, h is everything above the axis. So everything in y is of the form 0, y, and if you're above the x-axis, then y has to be strictly positive. So it's just the part of the y-axis that's above 0. And x intersect h, well, x is the x-axis, h is everything above the x-axis. So this is the empty set. There's nothing there. That's problem 7. Problem 8 was also on the review sheet. We want to prove the intersection of vector spaces is also a vector space. So just to make it concrete, suppose I just have 3 spaces, y1, y2, y3, subspaces of some vector space V. Think of it as Rn, but it doesn't. So 0 is in y1, 0 is in y2, and 0 is in y3, because every vector space and every subspace contains 0, so 0 is in y1 intersect y2 intersect y3. So 0 is in the intersection. Remember, subspace is a subset of a vector space that contains 0 and is closed under vector addition and scalar multiplication. Suppose I take vectors u and v, which are in y1 intersect y2 intersect y3. I must show that u plus v is in y1 intersect y2 intersect y3. But if u and v are in this intersection, this says u is in y1, u is in y2, and u is in y3. And if v is in the intersection, v is in y1, v is in y2, and v is in y3. But these are all subspaces. So if y1 contains u and v, then u plus v is in y1. And if u and v are in y2, u plus v is in y2. And if u and v are in y3, u plus v are in y3 is in y3. So u plus v is in all three of these sets. So u plus v is in the intersection. And if I take any scalar c in R, if u is in y1, y2, and y3, then cu is in y1, cu is in y2, cu is in y3, so cu is in the intersection. And this argument works, so that's the proof. And this argument works whether you have three subspaces, two subspaces, or infinitely many. All right. There are also a couple of problems on what looks like pages 17 and 18. So on pages 17 and 18, 1, 2, and 3. So you have the homogeneous equation, 4x plus 5y equals 0. You take 4 times 10 plus 5 times minus 8. That's 40 minus 40 is 0. So that means that the particular vector xy equal 10 minus 8 is a solution. And in fact, if you want to find all solutions, y is going to be minus 4x. So y is minus 4/5 x. So for any xy, no matter what x is, y has to be minus 4/5 x. So this is x times 1 minus 4/5 for any x. Or I could write this as x times 5/5 minus 4/5 for any x. I could factor out a 1/5 if I like. That's 1/5 x times the vector. I factor out minus 1/5. And that's minus 1/5 x times the vector minus 5, 4. And minus 1/5 x, that just means any number, because any number can be written as minus 1/5 times. So this is some vector, let's say t times minus 5, 4. So the solution space, it's all scalar multiples, t times minus 5, 4 for any t in R. Or if you don't want to use t, you can use the letter x. It doesn't matter what letter you use. And that's 5p. For part C, solve the vector equation x times minus 5, 4 equals 10 minus 8. Well, x times minus 5, 4 is minus 10x, 4x. And that equals 10, sorry, it's minus 4x. Sorry. X times minus 5, 4 is minus 5x, 4x. And that equals the vector 10 minus 8, if and only if minus 5x equals 10 and 4x equals minus 8, which means x equals 2. So the solution of this vector equation is just x equals 2. The next one is exercise 2. So we have the inhomogeneous equation. This is page 18, number 2. We have the inhomogeneous equation, 7x minus 3y plus 2x equals 6. And we want to check that certain vectors are solutions of the equation. So for example, what about 5, 9 minus 1? So is this a solution? 7 times 5 minus 3 times 9 plus 2 times minus 1. What is that? That's 35 minus 27 minus 2. 35 minus 27 is 8 minus 2 is 6. So this is a solution. And you can plug them all in and see all of those each of those 4 vectors is a solution. If you want to find the general solution, we can solve this equation. Sorry, this should be a z. We can solve this equation for z. We would get 2z is 6 minus 7x plus 3y. So z is 3 minus 7 halves x plus 3 halves y. And I divide by 2. So x, y, z is the vector 3 minus 7 halves x minus 3 halves y. Sorry. It's the vector x, y, and 3 minus 7 halves x plus 3 halves y. So I can write that as a sum of 3 vectors, 0, 0, 3. That's the part that doesn't involve an x or a y. The part that involves x is x0 minus 7 halves x. And the part that just involves y, 0, y, 3 halves y. So this is 0, 0, 3 plus x times 1, 0 minus 7 halves plus y times 0, 1, 3 halves. But again, I can, just because I don't like fractions, I can write 1 as 2 over 2. So then I can write x, y, z is 0, 0, 3 plus, and you factor a half out of this, I get x over 2, 2, 0 minus 7, plus y over 2, 0, 2, 3. And x over 2 and y over 2 can be any numbers at all. So x over 2 and y over 2 I can replace with x and y. I get some linear combination of these 2 vectors plus 0, 0, 3. And if I take the vector 1 minus 1, 2, which is a solution, 1 minus 1, 2, I want to write it in the form 0, 0, 3 plus x times 2, 0 minus 7 plus y times 0, 2, 3. Because this is a solution, and every solution is supposed to be of this form. What does this look like? If I add up these vectors, I get 0 plus 2x plus 0. That's 2x. The second coordinate is 0 plus 0 plus 2y. And the third coordinate is 3 minus 7x plus 3y. So I want 2x to be equal to 2, 2y to be equal to minus 1, and 3 minus 7x plus 3y equal to 2. 2x equal 2 says x has to be equal to 1. 2y equals a half says y has to equal minus a half. Let's see if this is correct. 3 minus 7x plus 3y is 3 minus 7 plus 3 times minus a half. This doesn't look good. So let me just double check my arithmetic. 0, 0, 3, 2, 0 minus 7, and 0, 2, 3. So I get 2x, 2y, and 3 minus 7x plus 3y. So this equation says up 1 equals 2x. 2x equals 1. So x equals a half. 2y equals minus 1, y equals minus a half. So this should be 3 minus 7 times a half plus 3 times minus a half. So that's 3 minus 7 halves minus 3 halves. That's 3 minus 10 halves, which is 3 minus 5 equals minus 2. Perfect. 3 minus 7x plus 3y, this is supposed to be minus 2, equals minus 2. So that's correct. So the linear combination is 1 minus 1, 2 equals 0, 0, 3 plus a half, 2, 0 minus 7 minus a half, 0, 2, 3. That's problem 2. And I'm going to squeeze problem 3 in over here. 3 is just to find the solution space of 5x minus 8y equals 0. That just says if you solve it, y equals 5/8 x. So the solution space is everything of the form 5/8 x, x, 5/8 x. So that's all scalar multiples of the vector 1, 5/8. So the solution space is all scalar multiples of this vector. That's all it is. And that is absolutely everything that was in homework 3. So let's turn to homework 4. So homework 4 is problems on page 22 to begin with. So exercise 1 on page 22, that's just more equations to solve. So for example, in 1b, you have 3x minus 2y minus z equals 0. So z is going to be equal to 3x minus 2y. So the solution space is vectors x, y, z, where x and y are arbitrary, but z has to be 3x minus 2y. And you can write that as x0, 3x plus 0y minus 2y. This is x times the vector 1, 0, 3, and y times the vector 0, 1, minus 2. So it's all linear combinations of these two vectors. That's all it is. And the other problems in homework 4